This is the Hungry Hound as intended, but does it always work this well? Please stay with me, as I present the second part of my Hungry Hound project. Hello everyone. Here's the second part of the Hungry Hound. I've made some changes and addressed the issues from part 1. Let me provide a quick description, starting from the back. We have this piece here, which serves as the tail attachment piece, connecting the tail to the main body. To attach it successfully to the main body, I've used M2 bolts and threaded inserts in the piece. If you're not using a servo motor, you might need to print 2 of these. Additionally, we have the tail lock nut, which also acts as a shaft for the tail. It screws into the tail and can freely rotate within the tail attachment piece. Thanks for joining me in this project. Let's keep going. Here, I have the battery holder. Unfortunately, one of the pillars broke while removing the support from the main body print. As shown in part 1, we have slots for the motor driver and the dev board. I'm quite certain this will also fit an Arduino Nano, considering that the Nucleo 32 dev board is slightly bigger than the Nano. Moving to the front, we have the DC to DC converter and the infrared module. These components are now installed in their designated slots, and we are good to go. Allow me to clarify that these slots are designed specifically for building this with DC motors. However, if you opt for the main body STL file with plain added to the name, it won't include these slots, only the upper screw holes. Now, let's get back to discussing the parts. This particular piece here serves as the cam for the back shaft. In the event that you decide not to use a servo motor, attaching this piece to the back shaft will still enable the tail to be activated as the back wheels rotate. On the cover, there's a power switch that controls power to the entire setup. Additionally, there's a slot here, which is for the battery charging connector. On the top, there is a lid that can be lifted with a screwdriver to access the charging cable, allowing you to charge the battery easily. It's understandable that the cables are still messy, and it's unfortunate that I couldn't implement a custom board for this project due to budget constraints. I will go ahead and screw everything together, and let's switch it on to see how it performs. Sometimes, starting with a basic setup can still yield exciting results and provide valuable insights for future improvements. I faced some difficulty when plugging in the power cable, but I managed to connect it eventually. Interestingly, I realized that a 180-degree rotation of the battery would have made the task much easier. Upon switching it on, I faced another issue: there was no power. After a short while, I used a multimeter to test the voltage, and everything seemed to be alright. Fortunately, I was able to identify the cause and address it later in the video. At last, the power came on, and it was time to box it up. However, before proceeding, I'll need to insert the battery charger connector into the dedicated holder, and firmly press it into the Hound's main cover. Regarding the battery, there is no over-discharge protection in place. To address this, I've opted to utilize a voltage divider connected to the ADC. The resulting output voltage ranges from approximately 1.4 volts, when the battery voltage is 6 volts, to 2 volts, when the battery voltage is 8.4 volts. When the voltage reaches the lower limit, the microcontroller will initiate a shutdown of all motors and enter shutdown mode. This constitutes the sole battery protection for this specific phase of the project. After securely tightening the screws, the next step was to install the head. This was done using a 3D printed rod and 3D printed nuts. Following that, it was time to conduct a charging test, and I'm pleased to confirm that it works as intended. Placing the top cover involves pushing one end into the designated slot and pressing it down until it lies flat. There's a chance it might audibly click into place, but that's not a guarantee. Regardless, it should fit snugly. If you encounter any issues, consider reprinting the piece using a layer height of 0.2 mm or less. Finally, the moment had come to put this to the test. However, before moving forward, I made a decision to address the issue with the switch. The slot designated for the switch within the main cover needed a slight expansion forward. To resolve this, I carefully trimmed it back just a tad, and this successfully resolved all the problems associated with the switch. Before delving into the firmware details, I want to extend my apologies for not releasing the firmware and schematic at this time. The reason behind this decision is that the current version contains some bugs that need to be addressed. The firmware is designed to enable the Hound to execute two primary actions: move forward at a set speed or remain stationary. When in the stationary mode, it can either move backward if an object comes too close to the IR sensor, or it can remain motionless. During forward movement, if the IR sensor detects an obstacle, the Hound halts, reverses its direction, and then executes a turn, either left or right. The specific action taken is determined through a random number generator, which is one of the peripherals on the STM32 MCU utilized in the project. Additionally, the duration for which the Hound remains in any given mode is also chosen randomly, spanning a range from approximately 8 to 100 seconds. The background operation of the random number generator ensures a continuous generation of random numbers, which are read and stored in a variable every millisecond. As for the tail, it maintains a consistent speed, but the distance it moves is also randomly chosen. Similarly, The duration for which it wiggles a specific distance is also randomly determined. Upon startup, the Hound initiates by selecting a mode or state randomly, along with a specific duration for which it remains in that mode. This is why you might observe me repeatedly toggling it off and on, to attempt to trigger different modes. One challenge to address is that the turning isn't executed as effectively as desired. Currently, only one tire turns, which could potentially pose an issue. Exploring the optimal turning strategy, such as moving one wheel forward and the other backward, or adjusting their rates individually, will be necessary to enhance this aspect. Furthermore, another aspect of the design needing attention is the wheel's inadequate grip. I'll need to find a solution to improve their traction. I want to express my sincere gratitude for your time and attention in watching the video. For the remainder of the presentation, I'll let the Hound operate autonomously. Sometimes, the firmware just ignore the IR trigger altogether. And did I mention that there's also a standstill mode where it moves backward and executes a turn upon an IR trigger? Thank you once again for watching this video. If you enjoyed it, please consider liking and subscribing to help support the growth of my YouTube channel.